Hey, good afternoon. It's great to be back amongst old friends from SpaceGen and lots of new faces, which is fantastic. Lots of renewal in the organization, which is exactly what it's all about. So thank you for being here today. It's wonderful. So last year, 2015, was an anniversary of the computer science industry. It was the 50th anniversary of Moore's Law. That prophecy laid down by Gordon Moore, the founder of Intel, in 1965, that computing power would double every 18 months or so. And things have been going pretty well for Moore's Law. We've rode that revolution throughout all of our lives to the point now where we have 1 billion transistors in our pockets and we're able to do amazing things with all of that. And it's been one of the underpinnings of the space industry. Moore's Law is starting to hit a little bit of a speed bump. I'm not going to say it's over, but it's having a rough time. I think I got some timing on there. I'll fix that. But it's hitting one of the fundamental limits of the ability to manufacture transistors. And that limit is the size of the atoms that they're able to place on the transistor. This is one of the most recent chips from Intel that is 14 nanometers across. And they're starting to count the number of atoms on the transistor to make sure there are enough electrons for electricity to flow across that. So maybe there's another way. Maybe instead of thinking about the atom as the fundamental limit of the transistor, what if we go inside the atom? Go to the next level down and look at quantum mechanics. Is there a way of using the unusual behavior of subatomic space to do computation? And that's exactly what a quantum computer is. This is an example of a building block of a quantum computer. This is a qubit, a quantum bit. It's built by a team at the University of New South Wales in Sydney, Australia. And that is a single phosphorus atom placed on a bed of silicon. So we're engineering at the nanoscale to put atoms exactly where we want them and then control circuitry around that so we can write to and then read from the behavior of that atom. Once we scale that up, put a few more atoms exactly where we want them, link them together and be able to allow them to interact. That's the fundamentals of a computer built on quantum mechanics. So this is a really exciting time for the computing industry. We've got a whole new architecture and a whole new approach in the way that we go about building computers. Since 1965 to now, we've had approximately 1 trillion times speed up in what we're able to do with computation. So what we were able to do back then, as part of the Apollo era, we can now solve those same problems on the supercomputers at the national labs about 1 trillion times faster. And so our dream is to take quantum mechanics on that next 1 trillion times speed up. So that in 50 years' time, when future SGAC people are sitting around here talking about the great old days of hopefully when we first went to Mars or back to the moon, they're talking about how they're able to solve the same problems that we had 1 trillion times faster using quantum computers. So there's a company out there called DWave Systems. They're based in Vancouver that have built like the minimum viable product of a quantum computer, and they've shipped it, and they've got a couple of customers. One is Google and NASA bought one together. Lockheed Martin and Los Alamos National Labs have each bought one of these computers. They use a different type of quantum computing architecture, but what you're seeing here is a chip with 1,024 qubits on board. Google released some benchmarking results just before Christmas, which showed that this chip was able to solve a particular problem 100 million times faster than a PC. 10 to the 8 faster. So we're almost there at the trillion. We only need to get to 10 to the 9 to do that. But one of the problems with this particular chip and this approach using the minimum viable product is that it can only solve one particular type of equation. So this is highly tuned to that particular problem, and we could get there that quickly. So what we're looking for is that explosion in universal quantum computing where we can solve much broader sets of problems and take on different challenges that can be applied to the space industry. So I want to talk about one of the attributes of quantum computing and some of the results that we get from it. So this is an example of some results that we get from the computer when my company writes to it. And we get these results back. And what you're seeing here is not one precise answer, but 3 candidate answers, 3 potential answers. And if you take nothing else away from today about how quantum computers work, know that quantum computers will find you an approximate answer extremely quickly rather than a precise answer in however long it takes. So get to one place, make a snap judgment, or get to the exact answer on a classical computer. That's what quantum computers are all about. So you can see on this chart, we ran this problem 30,000 times. That took us about half a second to run on the quantum computer. One of the candidate answers, the far left, we got about 22,000 times. The next one down, about 7,000 times. And the third one, the candidate answer, about 200 times or something like that. So for one particular problem, we didn't get one precise answer. We got 3 candidates with varying degrees of probability about how useful that could be. And this is really interesting. It leads us to the killer app of quantum computing in space. And this is, hopefully one day we'll see quantum computers being held like this in space. But to get to that killer app, I just want to take one more step back and talk about pattern recognition and machine learning. So all of us think about patterns in a certain way. It's how the human brain works. We're extremely good at quickly recognizing patterns and then being able to draw some conclusions from that. So this is a very simple pattern. We can all tell sort of what the basic design rules of this pattern were, and if the canvas were spread out, we could fill in the rest. What if the pattern gets a little bit more complex? We can tell as human beings looking at this that there are some rules underpinning its behavior. It's propagating outwards. And if we took a bunch of time and sat down, we could probably figure out what might happen next with this pattern. But it might be helpful to have a computer to help us out as well. What if it gets to the next level of complexity? Again, we can tell that there might be some underpinning rules and underpinning patterns in here, but it's impossible for a human to be able to determine exactly what's happening here. And this is where quantum computers come into play. Quantum computers can look across the entire solution set of interactions of patterns at once, keeping every possible solution in memory at the same time, and then giving us 3 or 4 potential candidate solutions to this pattern. So this is a quick example of some of the work that our colleagues at Lockheed Martin did recently on some deep learning and machine learning techniques in pattern recognition. On the left-hand side are the results from a classical computer. This is essentially how long it took, so time, to train up a system to be able to recognize patterns on a classical computer. This is how long it took to train up that same system using a quantum computer. So you can see that it's a fundamentally different approach and breakthrough approach to pattern recognition in these complex systems. What happens if it becomes even more complex? A complex natural system with many, many different actors that's constantly moving and constantly adapting and changing. As human beings, we're able to recognize that this pattern is occurring, but it's very hard for us to predict and react to this type of behavior. So when Google creates the self-driving car and they're trying to understand complex human behaviors in an environment like driving down the street, which is potentially one of the most complex things a human being can do, they need a new way to think about that problem that's based in probabilities rather than deterministic behavior of computers. And we think about driving in probabilities all the time. When you drive down the street and there's a kid bouncing a ball, there's some probability in your head that the kid's going to run out across the street with the ball and you have to slam on the brakes real fast, or that cab's going to turn out in front of you, or a myriad of other things are going to happen on a busy street. The same thing happens for a Mars rover. Right now, we program the rover to do exactly what we say in a deterministic fashion. We run simulations of its behavior back on Earth before transmitting the instruction set up to Mars. What if we had a different way of programming this system so that it behaved more like a human and thought more probabilistically about what it should do next? So should I go into this cave and explore this cave and understand what's in there? Or should I go over that ridge? And what are the probabilities around that and probabilities of success? And that's where a quantum computer can have some profound impact in the way that these machines that are a long way from Earth can react to a complex environment. Other applications in the space industry, looking at complex human systems in Earth observation. This is the harbour of Hong Kong. There are around 30,000 ships that transit Hong Kong harbour every month. Is there a different way to think about how those ships are going to interact and the type of behaviours that are going on there, and a way to handle that complexity of information? That's what quantum computing is hopefully going to have some impact on. And finally, as we think more about space exploration, some folks might know the odds of navigating an asteroid field are 3,720 to 1, according to C-3PO in Star Wars. And Han Solo famously said, "Never tell me the odds," because he was a human. He needed to, instead of deterministically plotting a path through that asteroid field, he wanted to be able to judge in terms of probabilities that complex adapting environment. My dream is that by Star Wars Episode 12 or so, it's always tell me the odds. Help me work in probabilities using a quantum computer so that machines, the future C-3PO, can help the human in a supporting way in understanding the probabilities of a complex adaptive environment like that and getting a result from it. So thank you very much for the invitation to be here today. It's great to be back.